Well, what's up guys, and welcome to part 2 on this video on momentum, impulse, and kinetic energy. In the previous video we went over momentum, kinetic energy, and change in momentum. Okay, and we covered those 3 concepts. So now we're going to go on to another concept which is also quite important and quite fundamental, which is elastic and inelastic collisions. Okay, so as you can see, we have 2 main types of collisions. So generally a collision is when 2 bodies or one body goes into a stationary wall or something like that, right? Everyone knows what a collision is, 2 cars even, but right now we're focusing on the single body collisions. Okay, so single body collision, so we only have one body, maybe let's say going into a wall or something like that. Okay, so if a collision occurs, there's 2 scenarios that can happen, right? If a collision occurs, the first scenario is that the kinetic energy after the collision is less than the kinetic energy before, or the kinetic energy before and after are the same. Okay, so if a collision occurs and the kinetic energy before and after the collision are the same, then the collision is elastic. Okay, and the kinetic energy is conserved, so the collision is elastic. Okay, but if a collision occurs and the kinetic energy before and after the collision are not equal, then the collision is inelastic. So basically we can summarize it that EK before and after are the same, then it's elastic. If EK before and after are not equal, then it's inelastic. Okay, mathematically we can represent this by saying for an elastic collision, EK before must be equal to EK after, and for an inelastic collision, EK before is not equal to EK after. Okay, and the one that we usually come across is this situation right here. This is the one because usually the collision actually takes in some energy, either in the form of heat. Actually, in the real world, that's what will always happen, but theoretically you could get an elastic collision. Okay, so let's actually jump into 2 or so examples just to make sure everyone understands this concept. So, examples. Okay, let's say that we have a bouncing ball has the following velocity time graph. Okay, so let's see. Okay, so we have velocity in meters per second, and we have time in seconds, and this is what the graph looks like. Okay, that's a bouncing ball, remember? So if you were to go over these points. Okay, let's just finish the graph. So right here, let's say this is 10, and let's say this velocity right here is 5. Okay, remember with a bouncing ball, let's say it's getting dropped here, then it hits the ground, then it's this is the impact happening across here, and then it leaves the ground, and then it basically rises or goes up and hits 0 again. So if we were to draw this, it would look maybe something like on an ST graph, it would look something like that. Okay, but that graph's not given, so that's if you wanted to draw it, it would look something like that. Okay, so the question is it elastic or inelastic? Okay, remember, we're focused with EK. So EK before equals a half mass times the velocity before the collision squared. EK after equals a half mass times the velocity after squared. Okay, but let's actually change colors. But a half m is constant, right? Therefore, EK is proportional to v squared. And from this, VB, okay, velocity before, this would be the point VB, and this is VA, so this is the collision. This is where the collision takes place. So the velocity before the collision is this point right here, and the velocity after the collision is this point right here. And we can see that velocity before is 10, and the velocity after is 5, so VB is greater than VA. Okay, and we've already said that EK is proportional to V squared. Therefore, we can say that the kinetic energy before the collision is greater than the kinetic energy after the collision. Therefore, the collision is inelastic. Inelastic. Okay, so that's the first example. If we were to go on to another example, let's use a bouncing ball again. But this time, let's have the ball look something like this. So we have a ball and we have the ground right here. Okay, and let's say it's got a mass of the ball is 1 kg, velocity initial, let's say, is equal to 5 meters per second, and then it hits the ground at some point, it comes to the ground, and then when it leaves the ground, velocity final is equal to, let's say, 5 meters per second. So we want to calculate, or we want to determine whether the collision is elastic or inelastic. Okay, so once again, we're going to say EK before is going to be our initial condition, equals a half mass times velocity initial squared. Okay, EK after the collision, or the final, is equal to a half mass times velocity final squared. Okay, and the mass, and again the mass and a half are constant, and velocity initial equals velocity final. Therefore, EK initial is equal to EK final. Then we can say, therefore, the collision is elastic. Okay, how else could we have done this? We could have actually just calculated, because we've been given a half mass times 5 squared. That's 25 divided by 2, which is 12,5, and units of joules. And on this side, it's the same thing. Okay, and then we can, from these solutions, we can come straight here. So we could have just analytically actually calculated it and come to the same conclusion. Okay, the last thing I want to do is one last example where we have a similar situation. Let's say we have a pool ball. Okay, and we have the barrier. Okay, so initially the pool ball has a mass. Let's say the mass is not given, and velocity initial is equal to, let's say, 2 meters per second. And then after the collision, or we can say it undergoes a collision. So then we have a collision with the barrier, and then we have the barrier once again. And after the collision, it's got the same mass. Okay, and after the collision, it has a velocity final is equal to 1,5 meters per second. Okay, so then we want to once again determine the whether the collision is elastic or inelastic. So we have to go to our kinetic energies. Ek initially is equal to a half mv initially squared. Ek final is equal to a half mass velocity final squared. Again, a half mass equals a constant. And therefore we can say that Ek is proportional to V squared. And from the values we've been given, velocity initial is greater than velocity final. Therefore, Ek initial is greater than Ek final. And therefore, we can say the collision is inelastic. Okay, so this second case wasn't very realistic, but it is theoretically possible. So yeah, so that's basically what I wanted to cover in this video, guys. I hope you found it useful, and I hope you guys are able to understand the difference between elastic and inelastic collisions. So thanks for watching, guys, and in the next video we will be going over the concept of impulse. Okay, so thanks for watching, guys. Hope you found it useful.